Okay, we have started off with talking about standard deviation. We then used the standard deviation in order to take the z-score. And so here we're going to use it again, okay, the concept of standardizing data, but we're going to apply something called Chebyshevs Rule to it. So let's get started. This is Chebyshevs Rule, and I've put it here in rather nasty mathematical language, and then I've restated it in what it means. But it's here we have, okay, the probability symbol. Okay, here we have, right, the formula for the z-score, and here we have a number k. And again, this is the same number k out here. So what am I doing? I'm saying the probability of this guy right here. Okay, what is that guy? This guy is, okay, we have the absolute value of the z-score, and we're saying that it's greater than or equal to k. So this is the event that the z-score, that the absolute value of the z-score is bigger than the number k. Okay, and this is the probability of that event. And so it's the probability that the absolute value of the z-score is bigger than or equal to k is less than or equal to 1 over k squared. Okay, if you're not confused, it's because you haven't been paying attention. Okay, just remember, this is all about that you can't get too many standard deviations away from the mean. That there are limits to how many standard deviations away from the mean you can get. If you set your standard deviation, say the standard deviation is bigger than this, there is only a small proportion of the data that is allowed to get any bigger than that. Okay. Think about the movie or the television show Star Trek, where Captain Picard says you can go this far, but you can't go any farther. That's the number k, and we can only get 1 over k squared of the data can get farther than k. So the probability that the z-score is larger than k cannot exceed 1 over k squared. So this 1 over k squared, it typically turns out to be a pretty small fraction, and so only a small fraction of the data can have a standard deviation that's very big. Okay. Having said all that, let me derive the formula. Okay, and I'm starting off here. The first line is just the definition of the population variance, and what I do from here to the second line is I do some algebra. I say divide both sides by sigma squared, and then multiply both sides by n. So this enables my sigma square and my n to change places. I then break up that fraction, okay, over the denominator to get this guy right here, because this reduces to this. And what is this? This right here, this is the z-score, right? Inside the parenthesis is the z-score of x1, and I would have the z-score of x2, etc. But I take that z-score and I square it. This is telling me I take the sum of the squares of all of the z-scores, and that adds exactly up to n. Okay, so this right here, I just recopied that last line. Okay, now here I want to get a handle, okay, on the number of z-score, the number of items that has a z-score that is at least k. Okay, we've said, okay, k is as big as we want to worry about, and so M would be the number of the items that are too big with respect to this, that are bigger than K. All right, so I have, this is the ones that bigger than K, and what I do from this line of the calculation to this line is, first I throw away all but the ones that are too big. Okay, the ones that are too big are at least K, okay, have a z-score at least K, and so I take that and I square that, okay, and that gives me my K squared. Okay, so what I have, this N then is at least as big as M times K squared. Okay, and here I've just, okay, rewritten it so it will be all together, and then I do some algebra again. Okay, I divide both sides by K squared, and I divide both sides by N, so I get 1 over K squared is bigger than M over N. Alright, that's this right here. But this M over N, that's just the probability, okay, that the absolute value of X minus X minus mu over sigma, the z-score of X, is bigger than K. So the probability that the z-score is bigger than K is less than 1 over K squared. Okay, so again, a complicated formula. You know, if you work hard, you'll be able to see how the formula follows. Now, what all does it tell us? Okay, well, let me take some real data here. Okay, I went to one of the departments and I looked at the classes that they were offering, and I looked at the number of students that they had in each class. Okay, that's this right here. I even included some of the research classes that only a few students enroll in. Okay, and so I took this data and I took the average. Okay, there are like an average of 17 or so students in class. Took the standard deviation, and I then took the z-score of this. So z-score of 40 is 2.43, etc. Okay, and then the z-score of 0 is negative 1.8. All right, and so forth. Okay. Now I took the absolute value of those. Okay, I went in, I took the absolute value, and then I did some counting. Okay, right here. Okay, this is the actual proportion of the data that is more than one standard deviation from the mean, or actually more than K standard deviation from the mean. This right here, this says like 30% of the data had a standard deviation bigger than 1. This says 2% of the data had a standard deviation bigger than 2, and this said that none of the data had a standard deviation bigger than 3 when we went in and counted. Okay, now this right here, okay, gives us the Chebyshev estimate. What Chebyshev said is, okay, you could theoretically have 100% of your data that had a standard deviation bigger than 1. Okay, it says that you could have 1/4 of your data, 25%, have a standard deviation bigger than 2, and you could have like 0.111, 1/9 of your data have a standard deviation bigger than 3. So what we have here is Chebyshevs Rule is never wrong, but it's much too conservative. Okay, it's never wrong, but it is much too conservative. Okay. And yet we can still talk about some things. We can do this exercise. suppose that a biologist collects 154 specimens of the southeast Kansas strip pit salamander. He measures the ulnas of each of these creatures and obtains an average of 12.34 centimeters and a standard deviation of 3.12 centimeters. What is the maximum number of salamanders where x minus 12.34 is greater than 30? Okay. Now this is a teacher example. Okay. What makes me say this? Because this right here and this right here are exactly the same. Okay. I'm cooking this up to get something that we can solve. Okay. So I start out with this event right here. The x minus 1.234 is greater than 30. I then divide both sides by the standard deviation. Okay. That gives me that this is now the z-score in absolute value, because I wanted something there that would fit into the Chebyshevs rule thing. Okay. Now I work out the math on this and it gives me here. Now I fit this into the Chebyshevs rule formula. This is just k. Alright. So k is equal to 1.96 and 1 over k squared is equal to 0.01. Okay. I take this 0.01, the 1 over k squared, and multiply it times n. So we have 1% of the data, times the number of data items. This gives me 1.56. Okay. So our data must be integral. We can only have like 1 specimen, 2 specimens, 3 specimens. So this says at most 1.56. So it can't be 2 like we would get if we were to round it off. So therefore there is can be at most 1 specimen whose ulna is of that size or bigger.